Okay, welcome to part 2.c of trying to present Playing the Confidence Game, an analysis of the relationship between surveyed levels of confidence and performance in high school algebra students. Today, we're going to talk about the motivation for this study, how we collected the data, some considerations about the data, and analysis of the data's structure. We're also going to discuss various models that we're using to try to make sense of the relationship between these two different data items. We're going to talk about that model's fit, as well as sensitivity to data perturbations, reflection on the model construction process, potential areas for further study, and lastly, a call to action. Motivation for why we're doing this. At the end of the day, we're trying to help teachers and trying to figure out a way in which we can connect. In this case, we're going to talk about confidence to mathematical learning outcomes. There's lots of literature looking at the connection between metacognition, which is thinking about thinking, and math learning outcomes. And that metacognition, that thinking about thinking, has direct relationship on math performance. And confidence is a form, it's a facet of metacognition. So you can see the connection between those things. And there's literature that also suggests that low levels of confidence, lead to math avoidance, which ultimately affects learning outcomes. And then studying student confidence, we can help to empower teachers, to develop strategies to mitigate low confidence. What did we do? We collected on the first day of school. I asked my students a series of icebreaker questions. One of these questions was to rate their level of confidence 1 through 10, 10 being very confident. And we're going to use first quarter grades to assess those learning outcomes. Grades for the quarter include both tests, quizzes, and homework. And the way that we're going to look at grades is on an aggregate total points basis. And you can see the mathematics of this. It's essentially the number of points the student has achieved divided by the total number of points possible times 100. Some things to think about. First and foremost, the data was collected in an all-boys Jesuit high school. There's some natural biases and lack of representation in the data. The grade data comes from a mix of tests, quizzes, and homework grades, and that's not homogeneous across the over 100 participants in this survey, which could also create some biases. We have a mix of different levels of maturity, freshman, sophomore, and junior boys, as well as varying levels of algebra. We have Algebra 1, which is all freshmen, Algebra 2 honors, which is a mix of all three, and Algebra 2 for struggling learners, which is just juniors. And then the next two bullet points here are what I think are actually the most important, is not only do the freshman boys come from a varied set of middle schools where there's no sort of control on the content that those boys have been exposed to heretofore, but also we draw from what is the largest level of income inequality of any census area within the United States. So the socioeconomic background, as well as the home life, is anything but homogeneous. And so that's going to have an effect on the ultimate data outcomes. We're going to think that all of those biases for expediency and modeling purposes, don't really contribute. But in fact, one area of further study would be to neutralize those biases. Some other kind of key modeling assumptions here is first and foremost, confidence is causal of math learning outcomes. And that we're going to propose a direct relationship between confidence and math learning outcomes, ceteris paribus. The data collected, as I mentioned before, is not representative, but we're going to assume that it is in order to make judgment calls about the relationship between confidence and grade outcomes. And we're also going to, one of the key sort of structural elements of these grades is that there's natural ordering, A is better than B is better than C, and so on and so forth. Looking at the raw data itself, you can see on the left-hand side, these are histograms of the collected confidence responses and the ultimate grades. Both of those are left skew, which that leads me to believe we need to look at things from a difference perspective. And sure enough, if you look on the far right-hand side, you see a histogram of the difference in confidence level and difference in grade, which appears to be more normally distributed. Additionally, in the middle, this is just a simple scatter plot, which ultimately ends up being one of our models, but you can see that there does look to be a positive relationship between the difference in confidence level and the difference in grade level on a student-by-student basis. So all of this suggests that we can come up with a direct relationship, between change in confidence and change in grade. Where it also, if you look at that change in confidence versus change in grade scatter plot, the differing breadth as well as the shape of the data suggests that potentially a down the ladder transformation might be in order. We're going to try two of those. And then lastly, as we mentioned before, the nature of the grade data, the structure of the grade data itself lends itself to an ordering, and we need to be able to account for that ordering in the model construction. So we're going to end up examining four models. The first three are linear regressions, and the fourth is a ordinal logistic regression. The first three start from a very, very simple change in confidence versus change in grade level. The second one, we try to perform a down the ladder transformation and develop this idea of a directional square root of the absolute change, where we take the absolute value of the change, take the square root, and then apply a polarity, positive or negative, to that square root of the absolute value. We did this because we wanted to capture the shrinkage that happens from a square root function in a down the ladder transformation. But obviously you can't take square root of a negative number if you're operating solely in the real number space. And so we needed to adjust for that. Model 3 is just a 1 over the change in the grade level, again, a down the ladder transformation. And lastly, this ordinal logistic regression. This is a type of logistic regression purpose-built for forecasting into categories that have an order and ranking to them. And naturally, our A, B, C, D, F has a preferential ordering that manifests itself. The way that we're going to look at goodness of fit here, because we do have structural differences, particularly between the different linear regression models and the ordinal logistic regression models, we're going to look at mean absolute error. So for each model, we end up predicting a grade outcome and then looking at that from an absolute error perspective relative to the actual grade. You can see here that model 4, this is the ordinal logistic regression, has the lowest level of mean absolute error. And in fact, even when we perform a sensitivity analysis and perturb the confidence level data, fit that data again, that doesn't really change the mean absolute error. So this model 4 with the ordinal logistic regression, this is the best model of the ones that we tried. And also to sort of back that up, when we construct that ordinal logistic regression, and the details are in the appendix, but the coefficient on the confidence level was positive with a p-value less than 0.003. So it's strongly robust, which indicates that there is a positive relationship between the probability that you're in a higher bucket for a higher level of confidence. And then also in the residuals, which can also be found in the appendix, there's no evidence of autocorrelation or heteroskedasticity. And like I mentioned before, when we do that sensitivity analysis and we perturb the confidence levels, you end up with a mean absolute error that is similar as well too, and the coefficient of confidence is still robustly positive. So overall, the ordinal logistic model is a good predictor of grade outcomes given a certain level of confidence. However, as we mentioned before, we didn't take into account that heterogeneity of either the classes or the courses. And some further work that we can done down the line is potentially turning that ordinal logistic model into a hierarchical ordinal logistic model where we can take into account those components. And then, as we mentioned before as well too, taking into account some of those biases, being an all boys Jesuit high school, the socioeconomic background biases, we can control from those. Those are potential some areas of further work that we can do down the line. And lastly, causality, big leap in this particular model. All we're showing here is that there is a relationship between the two, but we're not showing, for instance, that high levels of confidence cause high grade outcomes. And what would this be without recommendations? Ultimately, like what we've shown is confidence is a key factor in determining a student's performance in mathematics. So teachers should pay attention to this. And they can do this by using confidence as a formative assessment, collecting data on students' level of confidence, and then that allows them to create differentiated lesson plans to mitigate those low levels of confidence. And then just as a whole, teachers should look at creating a classroom of high confidence mathematics where they remove ego from the classroom, emphasize that everyone does in fact make mistakes, in fact, maybe even modeling that behavior of making mistakes, and then allowing for different learning styles in lesson design. And then lastly, maybe more importantly, is removing that role of rote memorization, the skills and drills that permeates much of high school mathematics, and focusing on the conceptual. Those are all things we can do to take that idea of low confidence out of the equation and really focus on high confidence mathematics. Thank you for your time.